We can use inverse matrices to solve systems of linear equations, and we can then use those to solve other problems. Before we get to that, let's look at an ordinary linear equation in the real number system, ax equals b. How do we solve this? If we have ax equals b, we are going to multiply both sides by 1 over a. You probably usually think of dividing both sides by a, but this is the same thing, of course. This is really a inverse. A inverse is the multiplicative inverse of a, or the reciprocal. What is a inverse times a? It's 1, which is the identity, multiplicative identity in the real number system. And so my x is equal to a inverse b, which of course is also b over a is another way to write it. We're going to approach matrix equations the same way. If A is an n by n square matrix, and if it has an inverse, x and b are n by 1 column matrices, then we're going to get the solution to ax equals b is going to be a inverse b, just as it was for real numbers. Let's work it out. If we start with ax equals b, now we are going to left multiply both sides by the inverse of a. Now, we have to be careful with this. In real numbers, we could left multiply, right multiply, the same thing, because in real numbers, multiplication is commutative, meaning we can change the order. Here, it's very important that we multiply on the left, because we want a inverse and a to be next to one another, because what is a inverse times a? It's the identity matrix I. When we multiply the identity matrix I times x, what do we get? We get x. That's the definition of the identity of an operation. When you perform the operation, the identity times x, the original x remains unchanged. That's why we call it the identity. Since that matrix multiplication is not commutative, we have to do left multiplication by the a inverse. And so our x is a inverse b. It is definitely not b times a inverse. In fact, you will not even be able to multiply b times a inverse. Let's look at an example. Let's solve this matrix equation. The matrix equation is set up similarly to an equation with real numbers, except instead of real numbers we have matrices. We still have our equal sign. And so here, this is the x. We can think of this as the a, which is really the coefficient matrix if you have a system of linear equations, and this b is a column matrix. So we are going to first find the inverse, because if that inverse exists, then x is going to be equal to that inverse times that right-hand column matrix. X is equal to a inverse b. So we want to use that shortcut for 2 by 2 matrices. First, we find the determinant. Remember, we multiply down the principal diagonal and subtract, and then go down the other diagonal. So we have 1 times 4 minus 3 times 1. Which gives me 4 minus 3, which is 1. So my determinant is 1. My inverse then is going to be the reciprocal of the 1. The way that we get this matrix is along the principal diagonal, the elements will trade places. So the 4 and the 1 will switch. Along the other diagonal, they will become opposite in sign. So we have a -3 and a -1. Multiply these by 1, and of course we will get 4, -1, -3, 1, just like that. So then my x1, x2 column matrix is equal to, here's my inverse, times that right-hand column matrix B. So when I multiply this, first of all, what are my sizes? We know that here's a 2 by 2. We just want to check and make sure this works. Here we've got a 2 by 1. My middle two numbers match, which means I can multiply them. And what size is my result then? 2 by 1. So we're going to get a column matrix over here. Let's work out the multiplication. If we do the first row by the first column, we're going to get 4 times 9 minus 3 times 6. When we do the second row times the first column, we get -1 times 9 plus 1 times 6. Work this out. This gives me 13. 4 times 9 is 36 minus 18. So 18, -9 plus 6. So -3. So my matrix equation then, the solution is x1, x2, 18 minus 3. Since my original equation was in matrix form, I'm writing my answer in matrix form. Now, a system of linear equations can be written as a matrix equation. Then we're going to be able to use inverses to solve that matrix equation, and then this will also give us a solution to the system of linear equations. Here's how we write this system as a matrix equation. My variables are here. My coefficient matrix is here. So 1, 1, 2, 3. And then here is my right-hand side, the column matrix 1, 3. Let's check this. When we multiply the first row times the first column, what are we going to get? We're going to get 1 times x1 plus 2 times x2. Then that's going to give me my row 1, column 1 entry, which is then got to be equal to the 1. When I do row 1, column 2, I get 1x1 plus 3x2 multiplying 1x1 times plus 3 times x2. That's going to go in my row 1. Sorry, that should be the second row, first column. Let me fix that. Second row, first column. We only have one column. I used the second row and the first column. And so I got 1x1 plus 3x2, and that's got to be 3. And so that matches up with our original system. Let's do another one. Here's a system with 3 variables and 3 equations. Okay, here's my x1, x2, x3. That's my column matrix X. Here's my right-hand side, 6, -4, 7. Let's write the coefficient matrix, and we're going to be careful that we leave zeros where needed. x1, what are our coefficients of x1? 2, -2, and 4. Now let's move to x2. We have -1, 3, 0. Now we move to x3. First row I get 0, then -1, and then +3. So there's my matrix equation. Let's go the other way. Let's write this matrix equation as a system of equations. Here we get 1x1 plus 1x2 equals 10. That's from the first row, first column. Now we're going to move to the second row, first column. So we're going to get 3x1 minus 2x2 equals 20. Now let's actually solve a system. Let's solve this system using the inverse of the coefficient matrix. The first thing that we need to do is we need to set up our matrix equation. So we have 7, 4, 2, 3. That's what we call our coefficient matrix. Here's my variables, x1, x2, and then my constants on the right-hand side, 11, -9. Now my x1, x2 is going to be equal to the inverse of the coefficient matrix times that right-hand column matrix. In other words, x is equal to A inverse B, which we've seen before. That gets us here. So now we need to find the inverse of that column matrix. So my A is this. What is my determinant? Seven times 3 minus 4 times 2, so that is 21 minus 8, which is 13. My inverse matrix then will be the reciprocal of the determinant times the matrix that we obtained by first reversing positions on the principal diagonal, and then the numbers on the other diagonal will become opposite in sign. So -4, -2. So this gives me an inverse matrix of, we have 3/13, we have -4/13, -2/13, 7/13. That's our inverse matrix. And so now we can go back to our matrix equation. It's going to be equal to, I'm just replacing this by the A inverse that I've now calculated. Okay. Okay, so I'm going to get a column matrix. I'm going to get first row times first column, 3/13 times 11 will give me 33/13. Then minus 4/13 times -9 will give me 36/13. When I move to my second row times the column, negative 2/13 times 11 will give me negative 22/13. And then 7/13, sorry, this should be 13ths right here. 7/13 times negative 9 will be negative 63/13. And then when I simplify, I will get 69/13, and I will get negative 85/13. Now we want to write our answer in the form that's dictated by the original problem. My original problem had variables x1, x2, no matrices in sight. So we are going to go ahead and write it as an ordered pair. x1, x2 is equal to 69/13, negative 85/13. Once again, just as if you had solved it some other way, you can check your solution by plugging these values into your original system and making sure that all of your equations are true. Let's do a 3x3 example. Let's solve this system using a matrix equation and the inverse of the coefficient matrix. So the first thing we need to do is we need to write our matrix equation. So here, 3, 2, 1 from my x's, then 2, negative 3, negative 1 on the y's. On the z's, we have negative 1, 1, negative 1. Here we have x, y, and z. Notice a matrix equation is not the same as an augmented matrix. A matrix equation has an equal sign in it. We have matrices that are combined using algebra, and there is an equal sign. So here on the right-hand side in our column matrix, we have 2 minus 2, 4 for our column matrix. So first thing we need to do is after that, is to find the inverse. How do we find the inverse of a 3x3? We write down the matrix that we want to find the inverse of. So here's our coefficient matrix. Then we augment it with the identity matrix. And now we're going to do row operations to where we get the left side to look like the identity matrix. And so the first thing that we want to do is we want to get a 1 here. And the easiest way to do that is to swap rows with the third row. Second row stays the same. Okay, and now we want to get zeros. Whoops, sorry, not right there. We want to get zeros here and here. And so we're going to do our row operations. I'm going to assume you're okay with how to do these. If not, you should go review that section. I'm going to skip some of the arithmetic here. So negative 2 times row 1 plus row 2 into row 2. That'll give us a 0 in the second row. And then negative 3 row 1 plus row 3 into row 3. That'll give us the 0 in the third row. And this is the matrix that you should get when you do your row operations. So now we need to get a 1 here. And that's easy. We just multiply that row by -1. My first and third rows stay the same. Now we need to get zeros in the second column. Remember, in each column we get the 1 first and then we get the zeros. So we need zeros here and here. So that means I will take positive 1 times the row with the leading 1. That'll be row 2. Add it to the first row and back into the first row. We'll take -5 times the row with the leading 1 plus the row we're working with, and then back into row 3. When you do this, you should get this matrix. Now we move to the third column. So the first thing we want to do is get our 1 right here. So we're going to multiply that row by 1/17. So my top 2 rows stay exactly the same. And then here I'm going to have 1. I'm going to have 1/17, 5/17, and -13/17 down there. So now we need to get our zeros. We're almost there. So we're going to do 4 times the row with the leading 1, which will be row 3, add it to row 1, back into row 1, and we're going to do 3 times the row with the leading 1, add to the row we're working with, and then back into row 2. This should give us a left-hand side that is the identity matrix. So 4/17, 3/17, and -1/17. Second row will give me 3/17, -2/17, and -5/17. Don't be surprised at getting fractions on these. It's pretty normal. If you don't get a bunch of fractions, it's probably because someone was being nice to you. Third row, 0, 0, 1, 1/17, 5/17, -13/17. So we finally have our inverse matrix. So my inverse then is the right-hand side of what we just found. And now, since we have x is equal to A inverse B is our general approach, and so I end up with this thing, x, y, c, here's my x, is going to be equal to that A inverse. Sorry, yes, we're writing it again. Times my right-hand side, and so now we need to go back up here and remember what we had before. See that column matrix with the 2, -2, 4? That's what we've got. Whoops. Two, -2, and 4. And so if we check our sizes, notice here we've got a 3 by 3, here we've got a 3 by 1, and so of course we will have a 3 by 1 column matrix. So here we're going to get 4/17 times 2, that'll be 8/17, 3/17 times -2, that'll be -6/17. -1/17 times 4 gives me -4/17. That's my top entry. Let's go ahead and simplify that. That's going to give me -10/17 plus 8, so -2/17 for my top entry. Now we move to the next one. Multiply the second row times the column, so that'll give me 6/17, multiplying the 3/17 times the 2, and then 4/17, and then 20/17. So 10 minus 20 gives me -10/17. Now we do the third row times the column. 2/17 minus 10/17 minus 52/17. And so that gives me -60/17. And so remember, we didn't start out with matrices. We started out with a system of equations in which we had x, y, and z. So we're going to write our answer as an ordered triple. So we get -2/17, -10/17, -60/17 for our answer. I sure hope this helped you understand how to solve systems of linear equations using a matrix equation and the inverse of the coefficient matrix. Good luck working